Welcome to Lesson 4B, Flux Chambers. A flux chamber, also called an environmental chamber, is a device that we use to measure the source strength. You can turn that into an emission factor. So what is it? It's some kind of an enclosure, a box around a source of air pollutant. They can be tiny, like the one on the left there. You can build a box yourself, or you can buy commercial ones. Here's an intermediate one on the left, and then a big one. There's a man for a scale, like a whole room. They're basically just a box, so any enclosure around a source can be used as a flux chamber. The way it works is you build your box, and when I say box, I've seen these actually be nothing more than a plastic bag around something. As long as you have some source inside, something that's causing the air pollutant, as we can see there, and then you have some flow coming in. So QA is the ambient air, and there's a CJA of the ambient air coming in, and then you have a blower of some kind taking the air out, and that air will be contaminated by the source. So there's a CJ coming out that's different than the CJ coming in. CJ will vary with time also, but generally we run this to steady state. And then QA is the same QA going out. We neglect any additional gas volume brought in by the air pollutant. So that's typically small compared to the bulk air. And then you have some kind of an instrument to sample it so you can measure CJ as a function of time. So what we're going to do is first I need to define some things here. So as I already said, CJA on the left there is the mass concentration of species J in the ambient air, where A stands for ambient. So if that ambient air is perfectly clean, CJA is 0. SJ, of course, is the source, and this is typically in, as we talked about before, in dimensions of mass per time. And then the other thing that we are going to assume here is something called well-mixed. And all that means is that, and you can see this fan here, you may or may not have a fan, but I draw a fan just to indicate that this is well-mixed. So what's happening is inside this chamber, we're mixing everything around with this fan, so that if you take a concentration anywhere in this box, we're assuming that it's the same everywhere. So CJ, as you see here, is a function of time, not of space. So CJ is not a function of where you're at. Now that, of course, is an approximation, because if you're right near the source, it's going to be a much higher concentration. If you're right near the inlet here, it's going to be a much lower concentration. But we're ignoring those points and saying that everywhere inside here, it's just a function of time. And then whatever comes out is kind of the average of the whole room. And so that's what you're measuring with your instrument. So that's what we mean by well mixed. And that's an important approximation that will make a lot in this course. So the bottom line is that the outflow CJ is the same as the CJ inside the flux chamber. And then finally, the sampling instrument, what it does is measures CJ as a function of time. And so how do we solve this kind of a problem? Well, we set up conservation of the mass of species J. Inside the flux chamber, we have some dmj dt, and that is equal to, how is the mass inside changing? Well, there's an inlet, CJA times QA. Remember, the mass flow rate of a species J is CJ times Q. So CJA, QA is what's coming in, and then there's also a source, and then there's the same kind of thing going out. So this is just a mass balance of species J. And what we'll do with the MJ is we'll let MJ equal CJ times V, where V is the volume. I didn't have that labeled here, but V is some volume of this flux chamber. So we'll let MJ equal CJV. And since CJ is the same, this well mixed, it's the same everywhere inside the flux chamber. So this is a constant within the volume. So we can basically remove that, take that out. So that's what I did here. So dmj dt is equal to dCJV. That's my typed volume, and this is my printed volume with a little slash through it. And then the right-hand side's the same. The CJ is a function of time, but the volume can come outside the derivative since it's a constant. And CJ is not a constant of space, only of time. So we can reduce this to V dCJ dt is equal to, and then the right-hand side is the same. And I labeled all these terms so that you can see what's going on. Every one of these terms has the dimensions of mass per time. And so you can go through and look at all the dimensions of each of these variables and convince yourself that these are all dimensions of m over t. And usually this is what is the unknown, and the reason we're using a flux chamber is that we want to measure SJ. So what we'll typically do is then we'll measure SJ, and then we'll define an emission factor. And so the emission factor is generally Sj over some appropriate denominator. And so we need to pick what's the most appropriate denominator here to make this EF. So that's exactly what we're going to do in these kind of problems. Now, first of all, we need to solve this equation. So how do we do that? Well, let's write this equation in what I'll call standard form, and we'll see this equation over and over again. So this is an important equation, a standard form for a first order ordinary differential equation. And that standard form, and you've seen this before, dy dt is b minus ay. You may have seen it in a slightly different form, but this is the form that I use. And so here our y is equal to cj. So whatever is the variable that's a function of time, we can use this. And so we'll write this equation again, this equation from here. I'm just going to divide through by volume V so that I get a dy dt, in this case a dcj dt on the left. So here we have dcj dt equal, I'm going to group all the terms that do not have a cj in them. So that's the sj plus qa cj comma a divided by volume minus, and then all the terms that do have a cj in them, qa over v cj. So you can see that that's exactly the same equation here. These two terms do not have a cj in them, cja, that's just a constant, qa, and then the sj. This one has a cj in it, so I just group those and divide by volume, and I get this form of the equation. And from comparing to this, I'll use color coding here. The b then is equal to this grouping, and the a is equal to this grouping. The negative sign's already included in the a, so make sure you don't get that negative sign mixed up. Once we have b and a, then we're in pretty good shape, because if we let this run for a long time, what's going to happen is we reach a steady state. So typically what happens if you're measuring CJ as a function of time, you start at the ambient because nothing has happened yet. And then what will happen is that this will slowly rise exponentially and then asymptote to some value, which we're going to call CJSS for steady state. So if you run this for a long enough time, you'll find that it flattens out. Mathematically, what happens is if you run it for a long enough time, as t goes to infinity, it levels off, CJ levels off. Therefore, the derivative, dcj dt, goes to 0. So the whole left-hand side goes to 0. The left-hand side of the above equation is 0. Therefore, we can write that the right-hand side, which in terms of the b's is b minus ay, has to equal 0. So b minus a, and our y, remember, is cjss, the steady state value. Once it levels off, so left-hand side goes to 0, and cj goes to cjss. And so we can write then from here that cjss equal b over a. And when we plug in our B and our A from these circled blue and green values here, you'll notice that the volume cancels out. And so what we end up with then is CJSS equal CJA plus SJ over QA, or what we really want to do is solve for the source typically. So it turns out that SJ is CJSS minus CJA times the volume flow rate QA, and this is also called M dot G. We use that notation sometimes as the generated source, the mass generation rate, and this is the most important equation then that we'll typically use. This is called the steady state source strength. And that's how you would calculate that. So mathematically, as I said, this is a first order dynamic system, which you have studied in previous courses. So we plot time and starting at 0, and we plot CJ as a function of time. And it goes from, I sketched this quickly before, but now let's do it a little more carefully. So it goes from some ambient value, CJA, to some steady state value. And if you're taking data, you would have data that like this, and there may be some scatter in this, and you keep taking data and it asymptotes to this steady state value at some time. Even if you don't have enough time to reach steady state, you should be able to figure out how to generate the steady state value just from these data points, plugging them into a curve fit. And we'll have some practice with that later on, perhaps in a homework. But I wanted to give you some other equations. So let's go back to the general first order. ODE behaves like this, and we had dy dt equal b minus ay. And if b and a are constants, then we can solve this analytically. And so we'll let y of 0 be the initial value of y. Y here is our CJ, but this is more general to apply to any first order dynamic system. And YSS is also y at time t equal infinity, which is the steady state value. And recall that that's equal to b over a. So at any time t, we can solve this equation. I'll call that 1, solve 1 at any time, not just steady state. And here's what you get. I'm not going to go through the derivation. We do that in ME 345. I think they call it something else. There's another number now, but your measurements and statistics class. So if you dust off your differential equations book or look this up, you will get this equation that I have starred here, which is the solution at any time. So y varies with time according to this exponential equation, where tau is the first order time constant, which is just 1 over a. So this all is related to this equation. And again, we're talking about letting y be our mass concentration, and we had expressions above for b and a. So you can do this in general. So that's how we're going to use this. And I want to do an example. So this is a very practical example. I have a nephew who runs a dairy farm, and they actually collect some of their methane like this and use it. So this is a practical for agriculture. Cows poop a lot, as you may know, and make a lot of methane. So there's cows in a barn making methane from their farts and from their poop, and instead of letting all that just go into the air, by the way, methane is a very strong greenhouse gas too. So we want to capture that and maybe use it for fuel. So here's how we have this set up. There's a big manure tank. I just have a box around part of it. So we put a box around it, make a flux chamber, make our own flux chamber. This could be just a plywood box. Again, I put the fan in to indicate well mixed, but you may not even have that. It'll still be pretty good approximation. And we do the same thing we did in the example when I was deriving this. We have ambient air coming in, QA. We have QA going out. We measure methane concentration, have a blower that kind of sucks everything through here. And the manure is, if you've ever been around manure, it stinks, right? Well, part of the stinkiness, a part of the gases that evaporate off of this manure surface is the methane, CH4. So here's the quantities that we measure. This tank is 2 meters by 1 meter. CJA is 0.02 milligram per meter cubed. That's the ambient. So there's some ambient in the barn there. We measure the volume flow rate of the bulk air, and CJ steady state. You run this for a long enough time till it levels off at 1.5 milligram per meter cube. And so let's generate an emission factor for methane from this manure pile. So how do we do that? Well, I'll list some approximations and assumptions. I'll abbreviate that A and A from now on, by the way. So that's something that we'll get used to. The air in the flux chamber is well mixed. So CJ outlet is CJ inside the flux chamber. It's not a function of space. It's a function of time. And then all the variables, that capital A and B, for example, are constants, and all these quantities are constants, the CJ, QA, and CJA, etc. So capital A and capital B are constants. And so it levels off, and we measure the CJSS, and now we can calculate the M dot generated, which is equal to SJ. And we gave this equation here before, so I just wrote it down. And let me plug in the numbers and get our answer here, our intermediate answer. And I get my SJ is 0.27 roughly milligram per second. But this is an intermediate answer because what I really want is the emission factor, EF. And so I'm going to keep 4 digits there, even though that's not my final answer. It's not that accurate, but I don't want to lose round off. So I need to calculate an EF as the M dot generated, or the SJ, divided by, again, some appropriate denominator. When I have in-person classes, I usually ask this as a poll question and have students give their responses. So you can think about this on your own here, since this is recorded. But which of the following is the best choice for an appropriate denominator? So remember, we have this flux chamber sitting on top of an area of manure, so a 2 by 1 meter area of manure. And so is the manure mass appropriate, surface area, volume flow rate, or number of cows in the barn? All of these are possible choices, and I just want to talk about each of these. The first one, manure mass, the depth of the pit, the manure pit, is not important in this calculation. It's important for the total amount of manure you have, But if you have a pit that's 10 feet deep versus a pit that's 2 feet deep, if this is fresh manure, it's going to be giving off the same amount of methane because it depends on the surface area, not on the depth or the mass or the volume. So we can say the same thing there. So the proper one is the surface area. It's an evaporation process that's giving this methane. So that's why the surface area is important. The volume flow rate is not important. In fact, you can change this to whatever you want and redo the math. You'll get a different CJSS and you'll get a different QA, but you'll get the same source strength. And then number of cows in the barn, well, that just determines how much manure you have. So the appropriate choice is that. And so once we have that figured out, we can calculate our EF. So I'm going to say an appropriate EF would be SJ over the surface area of the manure that we're measuring. So let's fill in those numbers. I plug in my SJ from up here that we calculated on the top, and then the area in the problem statement, it was 2 meters by 1 meters was the surface area. And then the rest is just unit conversions. A kilogram is 10 to the 6 milligrams, and then there's 3,600 seconds in an hour. So I get 4.85 times 10 to the minus fourth kilogram per meter squared hour. And I would round that to, we're really only good to 2 digits here, but I'm going to round it to 3 digits just to be consistent. So 4.85 times 10 to the minus 4 kilogram per meter squared hour is my EF that I measured from this flux chamber. And that's how this whole process works. And you'll have some examples to do in quizzes and homework. So make sure you understand these flux chambers. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.